Thank you, Flavio. Thank you for the introduction. Hello, everyone. My name is Advait Joshi, and I'm the CEO of DataSphere. Before we start, I will ask everybody a question. How many of you have a real-time data pipeline use case? In other words, do you work with real-time data today, and do you have a use case to analyze it in real time? We certainly do. We are in the payment space, and we are using HPCC systems to handle data in real time, which is very different than the traditional use case of doing batch processing. So I want to explain to everybody how we do this today. So we have a Roxy front end. All the web services that are developed in Roxy are available through ESP. And when a message takes place, or when a payment takes place, or when somebody uses their cell phone to transfer money from one place to the other, or when they use a card at a store and they swipe it, that message comes to us on a Roxy interface. And instantaneously, as soon as it hits Roxy, that message gets transferred to two places. It first goes to Kafka, and it then also at the same time goes to Elasticsearch. This is a little bit of a different architecture. The reason why we push it to both is we are able to maintain the entire message, the entire JSON string that we pass from Roxy to Kafka. We can actually pass from Roxy to Elasticsearch as well. Now, if you think about it, it gives us an advantage that the same message is replicated in both places. So if any one of these systems were to go down, we can actually pull it from the other system. Of course, Kafka is extremely strong, and it's meant to be hardened, so we can have multiple systems of Kafka running as well. But we felt that this was a better way for us to handle it, and it also gives the end user the ability to visualize this information as it's coming available into Elasticsearch, and they can see it through Kibana. Next, we actually pull this information into two databases. We maintain a small set in MySQL. The idea is that we want to be able to analyze some of this data instantaneously. Think about it as someone performing excessive volumes. So what happens if somebody moved tens of thousands of dollars in a matter of a minute or 2 minutes? We want to be able to know that. So we instantaneously analyze that in two places. We actually put that into MySQL, and 5 minutes later, it actually goes into Thor. So because Thor is more batch-based, we use Thor for doing periodic checks. So Thor is not the one who's actually handling the real-time transactions. It's actually MySQL, a combination of Kafka, MySQL, and Elasticsearch that makes this possible. Thor pulls the transactions back and reports on it on a timely basis. It can be 1 hour, it can be every 3 hours, it can be once a day. But anything that happens instantaneously gets reported through MySQL and Elasticsearch. We have actually developed what we call as a Sphere portal. A Sphere portal is nothing but a web frontend. It interacts with all of the components of HPCC systems. It can communicate with Thor. It can communicate with Roxy. It can actually communicate directly with Elasticsearch. It can feed into a Kafka pipeline. It can be a consumer of the data that's in Kafka. So it can actually go and pull the data from wherever it feels necessary, and it displays that data to the user. And so what data is the user looking at? They are looking at trending patterns. They're looking at things that don't look right. This is the time where we can actually also apply some real-time machine learning algorithms on top of it to figure out if the transactions that are going through the system are kosher or not. With having this architecture, it gives us tremendous flexibility to be able to pull information from wherever we feel necessary. In other words, you could have a transaction coming in real time, but I don't know information about that user over the last 90 days. That's the job that Thor does, where it will pre-compile, convert that into an index, and allow us to populate that in front of a user screen. So not only you're looking at a transaction that is going through, you're also looking at additional information about that user. So you're looking at history, you're looking at their patterns, you're looking at what these guys are actually doing, how they are doing it, what was the last transactions they performed, and so on and so forth. So it gives us tremendous flexibility to be able to pull this information back into Seer portal and give the user a single logon to access all of this information. The next question comes in is, how do you handle data redundancy, right? This is great. We have been able to handle all the real-time data. It's coming in from end to end, and the users are actually acting on that data in real time and near real time. Right? So we're actually cleaning it, ingesting it, labeling it, augmenting it. All of that is happening in real time. So how do you actually make it harder? So what we have done is we have actually used a very unique mechanism to make this happen. So we have, of course, 2 Roxy instances running, and both of those Roxy instances on the back end actually talk to the same DALI. So what happens is, out of the box, using a software-based load balancing, we get 2 interfaces in the front, and we're able to send the incoming queries on 2 Roxys. Now, of course, we can go to 3 Roxys, 4 Roxys, 5 Roxys, and so on and so forth. Sky is literally the limit. We can also have them talking to multiple parallel versions of DALI on the back end. We can also introduce hardware-based firewalls. We haven't reached that point yet where we had to have hardware-based load balancer running our firewalls, something like an F5. So far out of the box, we get a lot of performance. We also have 2 brokers running on Kafka. So all of our queues are replicated across 2 physical machines. Similarly, we have 2 instances of Elasticsearch running. So you have the same data replicated. And on the back end, we of course have 2 instances of Thor running. We also have, MySQL. The way we have implemented it, MySQL only keeps an interim amount of data, and we can actually pull it from anything else. So we don't see a real big need to replicate MySQL into 2 instances, because if I cannot make a connection to MySQL, I can quickly pull that data back from Elasticsearch or Kafka. So we don't need to replicate that. And the front end Seer portal, of course, is running on a load balanced Node.js server. So at the very lowest level, everything is running in pairs of 2s. Now, this doesn't mean that we actually run all these servers. It doesn't mean that we have 10 servers running. What we have done is we have repurposed some of those machines. When we actually first designed this, it was an interesting use case, and we went through some ups and downs. And of course, a lot of people from the community helped. Dan specifically gave us some helpers in how to make all of this replicate. So we use a open source library called Datapool, which is available on Git, and we replicate Thor on the back end. All of the data that is processed in Thor gets replicated on the second server on the back end. Elasticsearch, of course, allows you to do replication out of the box. Kafka allows you to do replication out of the box, and so on and so forth. So we actually run 3 physical boxes, and they're all bare metal. There is no virtualization on it. So we let all these services talk to each other homogeneously and use all the resources that are available. Some, of course, are CPU heavy, some are memory heavy, and some are disk IO heavy. The way we have designed our systems is the 3 boxes gives us enough redundancy, 3 physical servers gives us enough redundancy to recover from a single point of failure. Whether one disk goes down, or whether one service goes down, or whether one entire machine goes down, you have enough replication within the system and enough redundancy that you will be able to recover from it. Of course, as you go up and you want to have 2 points of failure, 3 points of failure, you want to have a very high-end load balanced system, this scales pretty easily. You can go from having 3 physical boxes to 4 to 5 to 6 and so on and so forth, or run this on a cloud-based infrastructure. In our case, we have found that we can tweak a physical infrastructure better than we can tweak a cloud infrastructure. And being in the PCI, PII realm, it gives us more control and more security if these boxes sit within a firewall. So whether you call it a private cloud or whether it sits in a client firewall. So I touched about PCI, PII. So what about security? How do we handle data security? So everything in this system is either encrypted or authenticated. You cannot connect to our Roxy firewalls without me knowing who you are. If you give me a username, password, I know who you are. You have to give me a digital signature. If and only if I can identify that digital signature, I can identify that, yes, you are a trusted device that is supposed to be sending information to me, only then that information is accepted in Roxy. Otherwise, it is rejected right then and there. When Roxy starts publishing to Kafka, there is, of course, all sorts of encryption and authentication going on. Similarly, when Roxy sends data to Elasticsearch, there is levels of authentication. So because we have multi-tenancy on Roxy, but we don't have multi-tenancy on Tor, which is also a very unique use case, which means I can have 10 clients coming in on Roxy, but on the back end, one client has their own Tor. We don't commingle the data on the back end. Because of that reason, we have to carry your digital identity and your authentications across in terms of data. So we use a same approach that most of the people out there use, which is a submarine approach. We have different handshakes going on at different point of times, and those handshakes protect us from compromise. So if somebody was able to get into Roxy, doesn't mean that they will be able to get to the actual data all the way to Tor. And if you really think about it, Roxy and Kafka only have data in motion. Tor, MySQL, and Elasticsearch is where the data is actually at rest. So obviously we use disk encryption, and we encrypt all of the data that is going in. For us, the main data that we need to encrypt is a person's credit card number, a person's social security number, and the personal information. We also use a different technique saying that if I just have a date of birth, or if I just have a credit card number by itself, it's not a PCI and PII violation. It's a combination of that information that makes it PCI and PII regulated. So we also separate our data sets separately, which means if you got access to one data set, you may be able to get access to a social security number. But that social security number by itself would not mean anything. You will not have the connection of the name and the date of birth with that. So that's how we use our data separation techniques, authentication, authorization techniques to keep our data safe. Of course, every communication that happens on the back end is TLS encrypted. So wherever the data is, those handshakes are very, very important. Everything in Seer portal that is presented back to the user is also presented in an encrypted manner and making sure you have access to doing what you're doing. Now, obviously, we have done everything we can do to protect these devices, but what happens if somebody still gets access to it? Well, in our case, most of our devices are running on a private network. They're not on a public network, which means whenever somebody is connecting to us on Roxy, they are not connecting through internet. So when I say that your cell phone is sending me data, it's actually routing that data through a central service, which means I only have to be available on a private network, and it will be the responsibility of the end client to route it from a public network to the private network. So that way we kind of keep all of our data secure in a fort, as may, and protect it at one place. The advantage of having all of this running in a very small environment, 3 physical servers is a very tiny environment. It gives us extremely high performance, high speeds, and high reaction times. It also makes it very easy for us to protect the data only at one place. We don't have to run around. Everything is at one place. So put all of your resources and energy protecting that. So that's the architecture that we use in order to monitor. We actually have clients that are using this system to do real-time transaction monitoring on payments, also on the cryptocurrency side. And as we grow, we will continue to push the envelope of where HPCC systems is used and how can we make it even more better. So how fast can we get, right? we actually did some numbers math, and we can actually get as fast as 25,000 transactions per second. Now, how do we do that? Is of course by having the hardware load balancers, having multiple nodes of Roxy running, multiple nodes of Kafka running, multiple nodes of Thor running on the back end, and we have done some architecture design and be able to come to this. And why do we need this? Right now, some of the peak volumes that we see in the industry are about 10,000 transactions per second. But if you look at Asia, the transactions are moving much faster because they're going from a cash-based to digital transactions, and they're all routing through a single payment interface in many cases. For example, in India, all of that is routed through UPI, which is a Unified Payments Interface. 1.3 billion people trying to go digital and transacting through a single payment interface. 25,000 TPS will be reached very fast. So you need to have something in place where you can have extremely high velocity and extremely high volume. And we have come to the conclusion that HPCC is actually able to handle it because it's flexible enough that it allows you to design your own architecture and make it in such a way that it will fit your use case. All right, so having heard this, would you consider using HPCC systems for your real-time data pipeline?
All right. Adwait, thank you so much. This has been a fantastic presentation, and as you know, we just love your use case. It's just very fascinating. So while you take a quick peek at the questions from the audience and prioritize those, we're going to take a quick look at your first poll. And so your question was, do you have a real-time data pipeline use case? And it looks like 83% have said yes, and 16% have said no. So for the 83%, hopefully you've been able to pick something up. And for the 16% that said no, I guess we'll find out if you would consider using HPCC systems when we look at that poll question. All right, Adwait, are you ready for the questions?
Absolutely.
All right. So the first question is, how will the new ML and HPCC systems help data seers?
So we identify ourselves as an AI platform, right? So ML is at the core. One of the things that HPCC systems helps us is, of course, clean and label and augment the data very fast, faster than anybody else. And then we are using the algorithms that are available for us today. But we constantly push the envelopes because let's just be honest, all of the algorithms that are publicly available are available for us as well as the fraudsters, which means if we are using them to stop them, they're using them to create more and more fraud patterns. So we will definitely be looking at creating newer libraries and pushing that envelope of what else can we do on HPCC. And we are very excited because we get a lot of support from the community for that and looking at our data sets because they're so very different from the rest of them.
All right, perfect. All right, here's the second question for you. How do you move data from HPCC systems to Elastic?
So this is actually very interesting. It's a part of a Git library. It's again open source, and it's Dan wrote the initial code for this, and then we modified it and we contributed back. It's moving the data through a Python library. So one of the beauties of HPCC systems is you can write Python code in it. All we do is we actually take the data set from HPCC, or rather ECL, and in ECL we write that information. We use Python to send it from HPCC to Elasticsearch. Since the library already exists and it's already published, all you have to do is provide a data set and an index name, and it will actually automatically send the data to Elasticsearch. So it's literally 2 lines of code and data is in Elasticsearch.
All right, perfect. Thank you. So I'm going to take a quick moment and look at your second poll while you look at the questions. And if anyone has any additional questions, this is the perfect time to send them in. So your second poll question was, would you consider using HPCC systems for your real-time data pipeline? And so, yay, 100% have said yes. We're thrilled to hear that. Thank you very much for participating in our poll. All right, here's an additional question. Do data seers evaluate other technologies before selecting?
I think I lost them. Hello?
Hello, I think we lost Jessica. So the question was, that's okay. The question was, did data seers evaluate other technologies before selecting HPCC systems, and what was your experience with that process?
Absolutely. We did consider other technologies before. I will be very, very honest. And I always tell this funny story that I had met Flavio a couple of years ago when he explained what HPCC was. And Flavio being so smart and him explaining what it was, I couldn't understand it. I couldn't keep up with his level. And so I was like, okay, I don't get this. I don't understand it. So obviously I went and looked at other things first. I looked into in-memory databases. I looked at Hadoop, Spark, Scala, all of that. I looked at some other document-based databases, some newer generation technology, Snowflake and stuff like that to see if that would help. The reason why we chose HPCC, because at the end of the day, you can use any technology that you want to use, right? It's literally like you're looking for a car. A Honda and a Toyota is going to do the job, but so is other American cars are going to do the job. But what is your experience? What is the specific use case? So for us, the specific use case was the ability to clean the data and label it and augment it, because a lot of times payments data is unclean and it doesn't come to us in a format that we want. So we just didn't want something that was able to handle the data at speed. We actually wanted something that allowed us to do the analytics at speed as well, cleaning and ingesting and all of that. So that was very important for us, and HPCC definitely solved that problem for us today. We are very proud to say this, that the amount of time it actually takes for our clients to upload the files to our system on an FTP server is greater than the amount of time we take to ingest that file in our system. So just think about it. It takes more time for them to upload this file to us than it takes us to ingest it inside our HPCC systems. And that was one of the reasons. And when we say ingest, we just don't mean that take it and spray it. We actually mean that we are cleaning it, we are mapping it, and it's actually becoming usable data. That's exactly why we chose HPCC systems, and it has been a great experience so far, and we have been one of the biggest advocates of HPCC systems out there.
All right, thank you so much, Adwait. All right, this has been a wonderful presentation, and if anyone wants to have more information on data seers, please check the HPCC Systems website under case studies. We've got a ton of information there, including links to several things that Adwait has done. Some talks we have on video and obviously his case study. So you can definitely find out more or on your website. Is that correct, Adwait? Any other place you would send them to?
Absolutely. You can tweet to me. My Twitter handle is aajoshi. You can find me on LinkedIn. I'm out there. So.
Yeah, and let me just say, Adwait is awesome to work with. So definitely reach out if you have questions.
Thank
All right,
you.
Adwait, thank you so much.